This video is going to cover the rest of section 2.6 and section 2.7. So we just have one more example about objects in freefall, and then we're going to talk about how to graph the motion of objects that are moving in one dimension. So before we get started, I want to point out that there was a mistake on the previous video, the one over section 2.5 to 2.6. In one of the example problems that I did. So if you can find the mistake and email me what it was and explain why it was a mistake, you'll get 2 bonus points on your quiz. So you have to email me before Monday. Okay, so moving on. Here's an example of where you can use symmetry when you're solving these problems. So let's say we have an object that was thrown upward on the edge of a cliff, comes back down, misses the edge, and falls all the way to the bottom. So how is that similar and how is that different from an object that's just thrown straight down at the same speed at which this one was thrown up? So this is asking, is the pellet in this case, does it strike the ground with a smaller, greater, or the same speed as in this case? So think about that for a second, pause if you need to. Okay, the answer is that it hits the ground at the same speed. And diagram C here is illustrating why. So using symmetry, we can see that on the way up, the pellet is going to decelerate. So the acceleration of this object the whole time while it's in the air is going to be equal to negative 9.8 meters per second squared. So as it's going up, it's slowing down, slowing down, slowing down, and then at the top, it stops for an instant. On the way back down, since the acceleration is still negative 9.8, this time it's going to be changing at the same rate that it was going up, except this time pointing in the downward direction. So by the time it gets back down here to where it started from, it's going to be going the same speed that it was going on the way up when it was at that same level. The difference is, of course, that it's now pointing downward. So if you throw the object up, it's going to go up, slow down, stop at the top, and then come back down. And when it reaches this point, its velocity here is going to be equal to the velocity it had at the same point going up, but in the opposite direction. So from here, if we just look at this motion from this point on, and compare it to this motion, we can see that it's exactly the same thing. So these two objects are actually going to hit the ground going the same speed. So symmetry is going to be a useful tool for you to use in solving equations. So not only is the speed at any 2 points that are at the same height going to be the same, but also the time it takes to get up is going to be the same amount of time it takes to get back down. So if you need to find, say, the total time that it took the object to get from here back to the same height, you could just find the time it takes to get up to the top, where we know the velocity is 0, so we know some information about that, and then double that. It's just going to be the same amount of time to get back down. Now, one thing where symmetry doesn't work is, say, if you take this height and divide it in half, this time here, we'll call this T1 and T2. T1 does not equal T2. Okay, and that's because at the top here, this is stopped, and then it's speeding up, speeding up, speeding up. By the time it gets to this point, halfway down, it's going really fast. And so it travels the second half of the distance much faster than it traveled the first half of its fall. So it's going to take more time to travel this half of the distance than it does for this half of the distance. So these two times are not the same, but if you're looking at the total time up and the total time back down to the same height, those two times will be the same. Alright, so let's move on now and talk about some graphs. So here is an example of a graph of position versus time. So time is always going to be our independent variable when we're graphing things with time. So that's going to go on the x-axis. And that's because time does not depend on the position. The position of the object depends on what time it is. So that's one way you can think about it. Alright, so here we see that we've got 2 data points plotted, and we've drawn a straight line through them, creating a slope. So if we find the slope of this line, as they're doing down here, we see that we would plug in the change in x, because that's what's on our y-axis, divided by the change in t. So that's a little bit confusing, because we know slope is delta y over delta x, the change in the y variable divided by the change in the x variable. It just so happens that on this graph, the symbol that we're using on the y-axis is x. Okay, so that's why we have change in x here, because that's what's on our y-axis. Alright, so anyhow, if we plug in the units correctly, that works out to be meters per second, which are the units for velocity. Interesting. Another way of looking at this is if you take this slope equation, change in y and change in x, and look at what's on the y and the x-axis, which actually is what's written right here, this is actually the definition for average velocity. Okay, so you could write average velocity is equal to change in x divided by change in t. Displacement over time. So what this means is that if you have a position versus time graph, finding the slope of the graph is equal to the average velocity. Okay. Next page. Alright, here's a graph of 3 different motions here. So we have a biker, and he's starting out going in the positive direction. So for the first 600 seconds, he's pedaling in the positive direction, and he goes 1,200 meters. So that's 1.2 kilometers. At this point, what is the graph indicating here? So from 600 to 1,000 seconds, the slope of this line is 0. So if the slope of the line is 0, that means the what is 0? This little 3-dot symbol, that means therefore. So if the slope is 0, therefore the velocity, average velocity during that period is 0. So in this period, he is resting. Another way of looking at this is the time keeps ticking along. If we were plotting little data points here, the time keeps going along, but his position is not changing. He's not going forward in the positive direction or backwards in the negative direction. He's just staying at the same spot. Alright, then over here, this time we have a negative slope. So now, as time goes on, we see that our position is decreasing, or we're going back toward the origin. So that means we've turned around and we're going backwards, or we're moving in the negative direction. So if you calculate the slope of this line, you're going to get a negative value. That indicates that we're going in the negative direction. We have a negative velocity. So here, our average velocity is going to be negative. Okay, so you should be able to look at a graph like this and interpret based on the shape of the graph and the slope what is happening. And then if we wanted to, we could actually calculate the slope of each line segment and determine what was his average velocity during those segments. Here's another example of a position time graph, and in this one, this is an example of somebody going not at a constant velocity or not a constant speed. So is the speed increasing or decreasing? So think about that for a minute. Would this be showing somebody whose speed is increasing or decreasing? So this is going to show somebody whose speed is increasing. If we look at the very beginning when the time starts, we see that the slope isn't very steep. As time goes on, the slope gets steeper, 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 steeper. So that means your value for velocity is getting bigger and bigger and bigger. So this person is speeding up, or they have a positive acceleration. That would be a more correct way to say this. So one way to think about this is to draw a tangent line at any given point. So the tangent line at a given point is going to be equal to the instantaneous velocity at that point. Or the slope of the tangent line, rather. Oops. I probably don't really need to write this since you guys can pause it and write down what I say. Okay. So if you want to find what the velocity is at different times, you can simply draw a tangent line at that point using a straight edge, not like this, and then calculate the slope of that tangent line, and that would give you what the velocity was at that particular time. And we can see here that this slope here is steeper than this slope here. That indicates that this person has a positive acceleration. The velocity is increasing in the positive direction. Alright, and the last graph we're going to look at is one where we're graphing something else. Now we have velocity versus time. So we could take this previous example. If we picked out enough points and calculated the slope of each tangent line, we could then come up with a set of velocities and times. So we could say, alright, let's draw a tangent line at 5 seconds, find the slope, and that would be our velocity there at 5 seconds. And then let's draw a tangent line here, find the slope, that would be our velocity at 10 seconds. So now you'd have a new data table of velocities and times, and you could take that and turn that into a graph. And that's what we're seeing on this next slide. So here's a graph of velocity versus time. I'm not sure if this is graphing the same motion that was on the other graph or not, but it doesn't matter. Okay, so here, if we think about what does the slope of this graph mean? Well, slope is, again, change in the y value divided by change in the x value. So on this graph, what's on our y-axis? Well, it's velocity. So we have change in velocity over change in time. And that should be familiar to you as the definition for average acceleration. So if you have velocity versus time, and you can find the slope of that line, and that would give you the average acceleration. Okay, so in this case, this is showing that we have a positive acceleration. What do you think it would look like for a negative acceleration? Think about that for a second. Okay, hopefully you've determined that that would just be a negative sloping line. What do you think this would look like for an object that was moving at a constant speed? So let's say this object is going at a constant velocity of 12 meters per second. What would that graph line look like? So that would look like, let's pick green here. If something's going at a constant velocity and we're measuring this, after 1 second we would measure their velocity and it would be 12. After 2 seconds we could measure it again and it would still be 12. After 3 seconds we would measure it again and it would still be 12. So constant velocity looks like a flat line on a velocity versus time graph. Okay, so one last note about these graphs is don't think that this graph is a picture of the motion. Especially let me go back to that other one of the biker. So a lot of people tend to look at a graph like this and think, oh, here he's going up the hill, and now he's riding along the plateau on the top, and now he's going down the other side of the hill. That's not what's happening here. This is a graph of a straight line motion. So you can think of him as moving back and forth along this axis. So for the first 600 seconds, he's going like this. For the next 200 seconds or 400 seconds, he's just staying right here. And then for the last time segment, he's going back this way. Okay, so don't forget that you have to look at this graph and interpret what that means in one dimension. Alright, so that's all there is for Chapter 2. We're going to do some more examples in class when you come back, but that should give you enough information to get started working on the homework problems.